that guy there. Turn this on. Okay, so I finally figured out a good way to introduce the dynamics, and we're really going to just skim the surface on dynamics here, because ultimately, when you're considered, Sydney can support this position. The MET program has an entire is it a 4-credit or 5-credit class relating to dynamics of simple kinematic systems.
I'm not sure, I haven't taken it yet.
Okay, well, I mean, typically when you're talking about dynamics in a general sense, and really you can't get much more general than the case of a manipulator, you're dealing with a class in and of itself. I mean, we're only going to just barely touch on what is going on within the dynamics of this manipulator. One thing I'll say is this morning I had planned to go through and watch the 2 video links that I mentioned yesterday in class. I did not have a chance to get that done this morning. I just kept on having people come in asking for help and stuff. In the morning, I really don't mind a bit if the robotics group comes in and asks for questions, because that's what I'm planning for, but I really try to keep the door closed to other classes just because I can't really afford to get off task. So as soon as I get those reviewed, one is a NOVA documentary, the other is a documentary on kind of the evolution of robots in military applications. It starts with the surge that they had in 2008 in Iraq, and talking about what they called an aero system. Essentially, it's just a mobile robot with a M16 attached to it and a camera. And given that it's not truly reconfigurable or self-contained, it's not really a robot. But the problem is a lot of people don't recognize or really understand what is meant by robotics. So I'm sure that you guys have seen that any number of times. People assume that something is robotic just because it has a microprocessor on it and it kind of does things by itself, but it really doesn't satisfy the definition of what a robot is. So I've already done that. So what we're going to do is update the objectives. Today we're going to go through and look at the dynamics of our system, and in introducing our dynamics we need to kind of have an idea of what we're talking about. Anytime we're talking about the dynamics, we're looking at the manipulator in motion. We've already kind of seen this in the second part of Lab 4 when we were planning that motion from point A to point B. That was a dynamic behavior of the robot. If we think about it, what do we have on that end effector, or on any of the joints or segments? Obviously we have motion, and therefore, since we have motion, we have velocities, accelerations, and in a physical system, forces. Okay, and those are the 3 primary things we're interested in when considering the acceleration, the dynamics. We're going to be looking at the velocities, accelerations, and forces associated with this. That's something we haven't looked at all up until now, because kinematics is all about looking at the state of the system without consideration to the forces that cause that behavior to occur. Okay? So if you recall from your physics class, I'm not quite sure where everyone is, we can say a couple things. We can say that velocity is nothing more than the change in position over some time interval. We can say that acceleration is nothing more than change in velocity over some time interval, which happens to be the second derivative of position, but that's something that I'll leave for your physics class. And finally, that force is nothing more than mass times acceleration which can be expressed as it is frequently as mass times the derivative of the velocity with respect to time. Okay. Let's see, where does this come in? This is, let's see, this is used for kinetic energy, isn't it? Because when we go through and integrate this term, we end up with 1/2 mv squared, which is the equation for kinetic energy. Okay, so this is the form that you'll often use when you're finding the, or deriving kinetic energy for a system. Okay, so with this, as an example, let's say that we've got a segment on our robot, or for that matter, an end effector, that's starting at position 0 and moving linearly to a second position. You don't really care what that second position is. It's just moving in a single dimension at a constant rate for a specific time. Okay? If you notice, if we have a situation like that occurs, what we see is a step response associated with the velocity. As soon as that movement starts moving, if it's moving nice and linearly, we have a step response because suddenly that segment or the end effector is in motion. Okay? Continues with a fixed velocity until it gets over here to the end, and at that point, suddenly we have no motion, so we have a step response as well. Okay? What's the problem with a situation like that? Does that truly represent a physical system? It can't. Why? Well, the red curve is our acceleration. You notice here, when there is no motion, there's no acceleration. Here, when the velocity is constant, there's no acceleration. And similarly over here, no motion, no acceleration. But what happens on these edges?
It attempts to hit infinity.
Yeah, it attempts to head off to infinity. Since force is equal to mass times acceleration, how much force is necessary to provide that, or how much force is necessary to initiate that movement?
Nearly infinite.
Near infinite, right? So this isn't possible. I mean, ultimately, even though that would be our desired behavior, that we can't achieve that. That means that if we want that manipulator to move, we can't just suddenly apply a specific torque or a specific step sequence to a joint. Okay? What we need to do is start it off nice and gradually so that when we run up the board here, I never checked to see if the thing was focusing. Let's hope it is. Seems to be. Okay. So what we would then need to do, and I'll zoom in on the little graph. Oh, come on. Okay. Guess we would have to come along here. And instead of immediately just start moving that manipulator, we would have to come up with a nice gradual start on that joint movement. And as we, well, there should be no bouncing around there. As we near the terminal point, we would want to have a nice, easy transition to that point. Okay? What's that going to do then for our velocity and our accelerations?
Smooth it out.
It's going to smooth it out. Essentially what we're doing is we're running each of these functions through a low-pass filter. Okay? And that's ideally, I mean, we saw in 313 and 324 that everything in life is about high-pass filters and low-pass filters. I mean, everything. So what we would see then is that our velocity function would end up looking something like this. It's going to come up here and something like that. Okay? Now you have to keep in mind that we might lag a little bit behind the tailing end. Okay? What we might have to do is, in order to make sure that everything is synced up properly, is maintain that velocity up until the very end in order to compensate for any tailing behavior over here, because this probably will not truly reach the destination position until somewhere beyond the end of the ramp here. Okay. Similarly, what's that going to do for our acceleration? It's definitely going to smooth it out. What we're going to see is that on the rising edge, we're going to have a, well, that's not correct, is it? We're going to have an acceleration curve that looks something like that. It's going to start when we're changing our velocity and after the velocity, the change in velocity returns to zero. And similarly over here, we're going to come along and have a deceleration that occurs as soon as the velocity starts to change again. Okay? So this is the practical velocity and acceleration curves. What's the forces going to look like? Force is going to be a scaled representation of which of those curves?
Acceleration.
The acceleration. So if we have a 10 kilogram mass attached to that end effector and we're trying to move it around, we know that we're going to require a mass to, or a force to get it in motion, a force to stop it. What's happening in here? The momentum has been established, and therefore, in this region here, there's no force associated with that. We have momentum in play. It is allowing the object to move from point A to point B, and after it gets to the end, then we need a counter force to stop that.
Are we just assuming perfect conditions on all this?
Oh yeah, absolutely. So, okay, so what does this kind of mean for us? If we have a point-to-point movement, not a real problem, right? Because if we have, say, point A here and point B here, I have no problem at all, gradually increasing the velocity until we have our running velocity here, and then gradually decreasing our velocity until we're back at zero here. Okay, it's not an issue. You guys agree with that? You notice that I kind of abandoned the note thing. I guess not, I still have notes on the board, so, the typing thing of the notes, so. I'm trying a few different things this summer since you guys are kind of guinea pigs and captive, so. But let's say that we have a planned motion. What are we going to find ourselves probably doing? By the way, what can you say the goal of a planned motion on a manipulator probably is? Generally, the goal is to get you from here to here as quickly as possible. What would be the point of maybe having this intermediate step here?
Go around something.
To go around something, right? So, or maybe this happens to represent the path of a weld or something like that that you need to perform, okay? But if we want to get from point A to point C as quickly as possible, what we probably don't want to do is speed up, decelerate, speed up, and decelerate, okay? we probably want to speed up here and decelerate here and stop here, okay? That makes sense? Now, this is kind of falling back on that high school physics teacher approach where I don't distinguish between acceleration and the vector that represents it, okay? Because we know that anytime we're changing direction, we're also accelerating. So what I'm talking about here is the magnitude of our acceleration, not necessarily the acceleration itself, okay? Okay, so if we don't want to do that, then what are we probably going to find ourselves doing? If we want to just accelerate to our running velocity here and decelerate to 0 from that running velocity here, are we going to ever actually make this point? We can come close, but what are we going to have to do?
Make like a curve.
Yeah, we're going to have to make a curve. So when we're going through and planning paths with an actual manipulator, what you'll find yourself doing, and I shouldn't say what you'll find yourself doing, what you'll find the controller doing is planning these paths so that it doesn't have to change the velocity of the end effector as it's moving through space. And in doing so, what'll ultimately end up happening is that we will go through and round the corners in each of our paths in order to maintain the same velocity and magnitude of velocity on the end effector. Yeah.
Is that kind of like the difference between like pick and place and like continuous motion?
Right. So if you have a pick and place, any of the pick locations or place locations are representing the endpoints. Those are the points where you have to have or have to be at 0 meters per second. Your velocity has to be 0 at those points. Okay. So those pick and place locations are definitely your destinations that you're trying to achieve. All of the intermediate steps in between there are all the points that just represent the path that we want to take to avoid obstacles. Okay. So for that reason, what we can do is we can, if we're trying to move from here to here, we can round off those intermediate steps as long as we're certain to arrive at the destinations that we're trying to achieve. Good. What I'm thinking about doing is, depending on how long the final programming assignment takes you, we're going to need tomorrow's lecture as well to formally introduce the linear interpolation method. You guys at this point could probably figure it out on your own, but I'll go through and describe how I approach it. But so tomorrow we'll need the lecture, and then I suspect probably Monday or Thursday and Monday we'll need as lab days. And then I'm thinking to fill out the week next week if we have the available time. We'll go through and look at setting up some pick and place processes on the Mitsubishi robot there. So that'd give you a chance to actually play around with it instead of just, you know, looking at it as you walk in the classroom each day. So, okay, so with that then, I was about to say something really cool, but I don't remember it. Okay, so just kind of keep in mind that almost always the destination is, destinations are the important aspects. The intermediate points that you use for planning your motion are usually there just to either optimize your path or to avoid obstacles. And for that reason, when that manipulator is in motion, it generally assumes a constant velocity and therefore rounds the corners. Okay. Now, another thing, and this is what I was about to say, is if we did not start turning here, what would our trajectory actually look like? Let's say that we definitely did want to achieve this point.
Overshoot it.
Yeah, we did definitely overshoot it. And this would represent what kind of system?
Continuous motion.
well, a continuous motion, but that would be, let's see, over dampened or under dampened?
You mean the like Chevy Chev versus
Oh,
versus
I mean, what we'd end up with is an undampened system at that point because we'd be overshooting and that would result in oscillation. So if we did go ahead and achieve that point, then we'd have to go through and overshoot it. And more than likely when we did so, if we had a perfect Chevy Chev response, then it would dampen and settle right out. But more than likely what's the other, let's see, there's Chevy Chev response,
there's
there's
Butterworth,
Butterworth,
and then
that's the,
that's like the perfect one.
that's the, yeah, the critically dampened response that we're looking for. The Chevy Chev is the over dampened, but it's, or the under dampened. The undampened response, I can't remember now, so. But anyhow, more than likely what we would do is not be able to come up with this nice critically dampened behavior. We'd probably end up with oscillation as we went through and pursued that second path. Okay, and each subsequent paths. Have any of you ever operated a forklift? Okay. Was yours a rear steer? And did you ever go out on wet pavement and spin it around?
Do a couple donuts real quick?
Yeah. So I did that one time unintentional. I went out to pick up a pallet of whatever and went out there and I started to crank it, and of course I turned. So I cranked it back and sure enough I ran myself right into a oscillating behavior. The only way I was able to get out of that was to stop. Because as soon as that back end starts whipping back and forth, it's just hard to correct that behavior.
Because you're holding on to it.
Yeah, no kidding, so. Okay, so the other thing that I want to talk about here is really the other big part of our dynamics consideration. And that is the torque associated with, or that must be applied on the joints in order to hold it in a static position or cause motion to occur, okay? The easier of the case, which is what we're going to focus on, is just holding a mass on the end effector in a fixed configuration, okay? And the reason for that is I don't really want to get into superposition and considering the motion paths and everything else associated with this. So let's talk about the torque real quick. Turns out that we have finally a use for that cross product that we talked about early on. The torque, which is defined by tau, is equal to the position vector times the force that is being applied on that arm, okay? So the position vector R is usually associated with some location, and so this is our R vector, and out here we have some force pointing off in some direction. And that force then is causing a torque to occur on our fixed end, okay? That torque corresponds with the holding torque that we would need to rate our motors at in order to prevent any slippage from occurring when we transport product from point A to point B. That makes sense? There's a couple things here. First off, what does that position vector R represent? In terms of our robot. This is the position vector from the joint that you're considering to the end effector. Okay, so that's pretty cool. And this is specifically, well, this is a general case, but what we're going to do is consider a situation where we have a mass on that end effector, the manipulator is in a static configuration, and it's just holding a mass in a static position. If that's the case, what's the force going to look like? The force that's acting on the end of that manipulator is going to always be pointed which direction?
You mean perpendicular?
Well, if it's in motion, absolutely, but if it's in a static configuration,
Isn't it towards the center?
what?
Is it towards the center?
Well, it'll be towards the center of the planet, right?
Yeah.
Because it'll be the weight of the object that's acting on it. So this force vector will actually be a weight, and we know weight is defined as the mass times the gravitational constant, okay? What's that going to look like in vector form? No x component, no y component. It's always going to be pointing due south. And let's see, what's the convention for weight? It's a negative energy, isn't it?
Yeah.
I can't remember. I believe like me standing up is a positive force, and the gravitation, the force due to gravitation is a negative.
Yeah.
Okay. So in this case, we would have a weight vector or a force vector that would be 0, 0.
Well, the mass is positive, the gravity is the negative parts, the negative, like 30, whatever.
Yeah. So we just go through, if we're looking at this in terms of the international units, that we'd be looking at newtons as our unit for weight, kilogram meters per second squared. We're not going to worry about any of the domestic, or not domestic, the English units, because I don't like slugs. So. Okay, so with that being the case, then the position vector is going to result in, let's say, something that looks like this, 2, 3, 4, meaning that it's, you know, running 2 in the x direction, 3 in the y direction, and 4 in the z direction. Okay. How are we going to go through and determine the torque associated with this? By the way, what do you notice about the torque? It's a vector quantity as well, right? And what are we usually interested in when we're weighting those or rating those motors? Not a vector quantity, a scalar quantity, right? So more likely what we're going to do after we determine the torque vector is find the magnitude of that torque vector, okay? And that's really nice and easy because that's what we're going to be looking at when we pick our motors, okay? And keep in mind, this is specifically relating to the holding torque on those motors, not the dynamic torque, okay? But that, I mean, if you can size your motors to satisfy the holding torque requirements, generally you got it, because that holding torque is the minimum torque in the system, and if you can design it for the holding torque, then you have everything else figured out. The only thing that you might be limited on then is your maximum velocity between movement positions. So. Okay, so in this case, we would have, let's say, a 10 kilogram mass up here, which would give us a 98 Newton force pointing due south. And we know that the torque is defined as the cross product of the position vector and the force. So we would have the determinant of I J and K, 2, 3, 4, and 0, 0, and negative 98. Okay, this is kind of cool. Those zeros do something for us, don't they? They get a lot of stuff to drop out. Okay, so in this case, let me go ahead and turn off the screen because I'm very obviously not using it for anything to distract myself with it. What we would see is, let me make sure I'm doing this right this time. I times the minor, so 3, 4, 0, negative 98, minus J times the minor, 2, 4, 0, negative 98, plus K times the minor, so 2, 3, 0, 0. So we end up with, oh, let's see, that would be 294, negative 294I, plus 196, plus 0K, and that represents our torque vector, which would just be negative 294, 196, and 0. Okay. How then are we going to use that to actually, by the way, what are the units on this? What do we usually associate torque with? Usually associated with work, right? Okay. Work has units, well, work is what, force times distance?
Yeah.
Gives us the units of Newton meters. Well, when you look at your torque wrench, sure enough, the units on that torque wrench are the same, Newton meters, okay? So the units on our torque vector are going to be Newton meters. So our torque vector in this particular case is negative 294, positive 196, 0. What's the magnitude of that torque vector going to be? How are we going to go through and determine the magnitude?
The square root of each of the numbers squared out together.
Yeah, I mean, distance formula again, right? It's amazing how often that distance formula comes up, okay? So we're just going to go through and say that the magnitude is equal to negative 294 squared plus 196 squared plus 0 squared if you're into putting such things in there. I actually had a student this last spring in my 221 class that had to ensure that the zeros were in the solution process, so. Just one of those people that was really on top of the details, so. For me, I don't really care, zeros are overrated. Okay, so what do you guys,
353.3.
so 353.3 Newton meters. So we would want to rate that motor so that the minimum holding torque was 353.3 Newton meters, okay? Now keep in mind that sometimes this is rated in Newton centimeters and oftentimes in inch pounds. Yeah, inch pounds or inch ounces. So if, depending on the different manufacturer, you'd have to go through and probably do a conversion in order to get it back to the appropriate units of your vendor, so. Okay, so in this case, if the position vector is running out from a joint to the end effector, well, what are the different scenarios? Are we going to always see the situation where the position vector from the base frame to the end effector is the longest position vector? generally you would expect it to be, but that's not always the case, right? Okay, that means that it's entirely possible to have more torque on one of the joints that are further in the chain than is on your base frame, okay? So as an example, let's do a couple of things here. I'm going to go ahead and erase this real quick. And by the way, if you can figure out the angle of separation, you can use the, it's not the law of cosines, that's wrong. It's, you can use the magnitude formula for vectors. It's the magnitude of r times magnitude of f times sine of the angle between them. But for me, it's just always easier to calculate the vector quantity and then find the length of that vector quantity, so. Okay. So let's do a couple things real quick so that we can really start to consider this. Let's stick with the same 10 kilogram or 98 Newton weight at the end of that end effector. Our position vector R1, we might, well, let's just go ahead and go with what we had before. Gives us a position vector of 2, 3, 4, meaning that the magnitude of our torque was 353 Newton meters, okay? If the position vector from our second joint out, I don't know, R2 then, looks like it's probably something like 2, 0, 0. You guys agree with that? Why don't you go ahead and find the torque associated with the second segment real quick, and then we'll look at a situation where we don't have, or don't necessarily always have more torque on the earlier joints. By the way, what would be a good configuration to determine the holding torque for each of these? Just as kind of a matter of practice. Maybe if we extended those arm segments horizontally and applied a force at the end, we could probably go through and progressively rate each of the torque specifications of those motors, okay? Again, this will provide us an idea of what the torque specifications will be, but it does not mean that we won't run into a situation where the initial joint has the most torque applied to it. But in general, if you go through down a manipulator chain, you'll find the largest motor on the earlier joints, just because of the torque specifications that go along with it. Okay, so how much torque is being applied to the second joint? Let you guys do that real quick, and I'll go ahead and grab a few stepper motors so you can take a look at them.
Everything is zero.
Huh?
Everything else is zero, except for the negative 1 and 6. Huh? This is a quiz, it's easy.
Did you do it already?
Did you get that to work out?
Did you just get 3 and 3?
A parentheses. So, single parentheses.
Not sure that,
We spent a long time just finding a single parentheses that was off.
I was closing this square root early, I was closing right here. So only did the square root of that, so it was, the only reason it worked was because it land on it, right?
Okay,
No.
196.
yeah, so.
I think we get, like most people got, we're just kind of spacing out.
Yeah, surprisingly, that should have taken none of us any kind of real effort, so.
Yeah, 196 minus 0 plus 0.
Yeah. Okay, so we see the magnitude of the torque on the second joint is just going to be 196 Newton meters. And so what we then see is that in this particular case, as we expect, the first joint is going to have the most torque or the highest torque requirements. Second is going to have the a progressively lower torque requirement. But as I mentioned, this isn't always the case. If we have a situation where we have the manipulator setting something like this, and let me draw it more like this so that we have that first segment as the longest segment. Let's say that the first, we're still dealing with same 10 kilogram or 98 Newton weight hanging off the end there. But in the first case, we have a position vector R1 equal to, let's say that looks something like 1 over 1, we'll say back 1 and up 5. In the second case, we have a position vector that's nearly horizontal, R2. Let's say it's going to have X and Y, so what, maybe 5 and 5 and negative 1. In this case, we can see that the magnitude of R2 is definitely longer than the magnitude of R1, okay? And for this reason, we're going to have a situation where the torque requirements for the second joint, or the torque being applied to the second joint is much greater than that being applied to the first joint. So just a kilowatt hour, go ahead and figure out the torque. That way, when you run into these problems on the FD exam, you can do them real quick. So
Is this the type of question they legitimately ask about torque?
yeah, they absolutely do. So you go through and you have to calculate the torque, and then you need to figure out the magnitude of the torque. So don't drop it on your toe. By the way, if you notice on there, typical stepper motor will tell you the stepper resolution, the torque, specifically the holding torque, and then the voltage and current specifications for the holding torque. That voltage and current specification is the power requirements to hold that motor in a fixed position, okay? Well, here in just a second, after we do this, we'll go through and talk about how you get a stepper to turn. you guys find the magnitude there. Okay, so. Oops. And actually, I bet I can go through and say that the magnitude of channel 1 is going to equal 98 times square, or 98, yeah, times square root of 2. And same thing over there for 90 times square root of 2. So about probably real close to 140 here and 600 over there. Maybe 650 over there, so. What's it turn out to be?
I got for R1, it was 138.6,
138.6.
and R2 was 692.96, so 693.
693. Okay. Now, like anything else that you're designing, you're going to want to take these and multiply them by, say, a 25% safety factor or whatever else. If you did have to go out and choose a stepper motor, you would never go out and pick a 140 Newton meter stepper motor to satisfy this requirement, okay? You would probably go out and choose, 125% of that, which would be, what's that times 1.25? And keep in mind that this is just the torque specifications for this particular configuration, so.
It's 173, so 175.
So you'd probably choose a 175 Newton meter motor there, if you just want to sustain this configuration. And then over here, same thing, multiply this by the same 125. When you're going through and designing these, again, generally in order to actually choose the motors, you align all of your joints horizontally. That makes the calculations really nice and easy because ideally you'd be aligning them along either your x-axis or your y-axis, okay? Therefore, when you go through and let's say that you do have a horizontally aligned manipulator, the math turns out super nice. Okay, let's say that this position vector, R1, is 2, 0, 0. Oops, that's not right. R1 is the distance to the end effector. So this might be 6, 0, 0, okay? This then would be R2. 4, 0, 0, and in this case, I'm just assuming that each segment has a length of 2 meters. And then finally, our third position vector is 2, 0, 0. Well, what do you notice about the cross product when you go through? 2 of those determinants go to 0 because you have 2 zeros within your matrix. So ultimately, then it just turns out to be, to find the magnitude, it would just be the 2 meters times the maximum payload on the end effector. Okay? In the case of our robot there, that Mitsubishi can handle, I think, 19 point, it's just shy of 20 kilograms. I can't remember quite. I mean, it's a pretty sizable load, so. So with that being the case then, we could go through and determine what the motor specifications more than likely are just by going out and measuring the length of each joint and determining what the current or the torque specifications are. Now notice on the base joint, the base joint is aligned vertically. So how would we go through and determine the torque requirements on that base joint if it's aligned vertically instead of horizontally? Because obviously if it's aligned vertically, we're not going to have to consider or concern ourselves with the torque, specifically the holding torque. In that case, what we'd have to do is take into consideration the shaft diameter and the bearing sizes and everything else, because then when you're, supporting this on a vertical shaft or in part on a vertical shaft, then you'd have to make sure that the bearings and the physical construction can handle that force that's being applied to them. Good. So I hope this gave you a good idea of how to go through and look at that in order to, I know that every so often someone wants to do a robotic type project for their senior project, but they never really have a good idea of how to go out and start picking motors. Well, it really comes down to a very simple process like this where you're going to go through and come up with some static configuration to figure out the torque parameters that you need in order to pick your motors. So, good. The other thing is, you guys of course notice that there are 6 wires on this particular motor. In general, there's 2 different configurations for a stepper motor. There's what's known as a unipolar and a bipolar configuration. Okay, so one of 2 alternatives has this configuration. Generally, you see this as a 4-wire configuration. And let me just bring up the notes on this real quick. We're Tennessee people. Some guy in Tennessee was arrested for threatening Obama. For some reason, you would suspect, even in Tennessee, you'd recognize the fact that that's not a good idea. So, I mean, in Kansas, and we're not far above Tennessee, we know that. But okay, so. Give me just a second here. Okay. Good. Okay, so in this case, we have what's known as a bipolar stepper motor. So bipolar stepper motors are generally identified by 4 leads. Okay, and why do they refer to this as a bipolar stepper motor?
Because the two inductors.
Well, there's 2 inductors, but the bipolar behavior comes from the fact that we're going to be reversing the current through this inductor, therefore swapping the pole on that inductor, okay? So when you go through and look at this, the step sequence for this particular motor, what you're going to see is that you will have a positive voltage and ground. Oh, geez. Okay, and then of course ground and ground. And then you're going to have a situation where your positive voltage moves to here. I'll label these A1, A2, B1, and B2, so that we can go through and create a timing diagram out of this. So in the next step, what will happen is that your positive voltage will move to A2, and ground will move to A1. Subsequently, your positive voltage will move to B1. Subsequently, your positive voltage will move to B2. Okay, so if you have A1, A2, B1, and B2, your timing diagrams are going to look something like this. Okay, and what this is going to do is cause a north-facing pole in this first step, a south-facing pole in the second step, what we can consider a north-facing pole in the third step, and then a south-facing pole in the fourth step. This is what's referred to as full-step mode. There are also half-step and micro-step modes as well, but we're not going to talk about that. One of the nice things that has been developed are stepper motor controllers. Okay. With this, what we would end up doing is using an H-bridge in order to control this. An H-bridge would just place each of these coils between, very literally, a transistor bridge. And then what would happen is that this would be on. These are nothing more than electronic switches here. And on when we want current flow one direction, and then vice versa. We turn this one off and off, this one on,